Can everybody see my screen now?
Yeah, that's perfect.
Okay, cool. Well, thanks for the introduction, and thank you for having me here. I'm very excited to be able to give this talk here. So my name is Martin, indeed. I'm co-founder at SecMed. Previously, I was at Stanford. I left Stanford in May to really go full-time for my startup, SecMed. What we do at SecMed is we do curate data for artificial intelligence with a focus on medical imaging. So during this talk, I'm really going to focus on the medical imaging piece, especially radiology. So I'm going to talk about how to curate your data to make it ready for artificial intelligence development. My disclosures are that I recently got a research grant from the American Heart Association, and as mentioned before, I'm a co-founder, I'm an employee and a stockholder at SecMed, and this is a relevant disclosure since SecMed actually works on data curation in medical imaging for machine learning. So we all know that there are a lot of opportunities, a lot of options for machine learning and deep learning in the medical imaging space. These different opportunities are throughout the whole spectrum of areas in the medical imaging acquisition and analysis spectrum. So it starts with indication and patient scheduling, where AI can have an influence. Then we have acquisition, where AI can optimize, for example, the duration of MRI sequence acquisition, optimization of image reconstruction and image quality, and of course, automated segmentation, quantification, and radiomics, and classification and reporting. And as a last step, AI can also have a significant influence on or impact on prognosis of certain diseases. And of course, in the end, we would like to see that AI is going to influence or going to have an impact on each of these different pillars, because then we can see the true effect of artificial intelligence. So it's really great to see that there are many opportunities for AI to actually have an impact on the medical imaging space. However, when we actually look at the clinical implementation of AI, we see that this is very limited at this moment. Why is that still so limited? So that's one of the questions that some of my colleagues and I tried to answer in a large survey, which we did in Europe and also outside of Europe. And one of the questions that we asked to more than 1,000 radiologists and residents, what do you think are the hurdles for AI implementation? And oh, I see this actually lined out a little bit skewed, but anyway, it doesn't matter. The biggest thing that was mentioned was the ethical and legal issues. And another one was lack of knowledge of machine learning, in particular, 56%. And then if we zoom in a little bit, we can see that quite a few people also mentioned the lack of generalizability of AI software. And then only 15% mentioned a lack of high quality image or heterogeneous image data. And I think there is a discrepancy, because if you want to develop a generalizable AI algorithm, you will need to train it with heterogeneous and high quality image data. So this discrepancy is probably because this survey was done with radiologists and residents that are not doing machine learning on a daily basis. This is just done by radiologists who are doing their clinical work on a general basis, but are not the experts in machine learning. So it's interesting to see that the knowledge with regards to the need for high quality and heterogeneous data has not gone that far yet into the radiologists and residents. And I think it was mentioned in the previous presentation as well that everybody wants to focus on the fun work, the actual model development. However, before you can develop your model, before you can start training, testing, or validating your AI algorithm, you need to curate the data, and that's much more work than the actual model development. And once you have developed the model, then actually there's an extra step, and that's the deployment of the model, which is even more work. But at this point, let's focus on the data curation piece, because once we have done this, then we can start with the fun stuff, which is the model development part. So why would we actually curate our own data? Why not just use public data? Because actually there are quite some public data sets available. There's the Cancer Imaging Archive. There are RSNA Kaggle Challenge data sets available. And also at Stanford, multiple data sets have been made publicly available. And the quality of some of these data sets is pretty good. especially if you want to develop an algorithm just for a research paper, or if you're writing a grant proposal, for example. But if you really want to develop an algorithm that's going to be commercially used, clinically implemented, then you will need more than just these public data sets. Here you can see another list of more data sets that are just publicly available, and some of them are relatively small, but some of them actually are really big, like the National Lung Cancer Screening Trial, 26,000, and here the Chexpert chest radiographs data set, 65,000 exams. So some of them are actually really big, and they're really nice to play around with. So if you decide to not use a public data set, but actually curate your own data, then that's what this presentation actually is focusing on. So how do we do that, and what are the issues there? So first of all, very commonly, the issue is that people are using relatively small sample sizes for the development of their AI algorithms. And why is that an issue? Well, let's look, for example, at this theoretical data set where each point means a different person and they all have different characteristics. So let's say you start training your AI algorithm in this population here. And then you want to validate how this algorithm works in a different population. And you can imagine that then you get problems. So this is called bias. So you train your algorithm on a certain data set, and then you try to evaluate it or use it or apply it in another population. And then your algorithm all of a sudden doesn't work as good anymore because it's used to these patients, but it's not used to these patients. So diversity issues are very big if you only use a very small and not heterogeneous data set. So here you can see an example. These are two different algorithms that were trained to detect COVID-19 on chest X-rays. If you run an algorithm, if you validate an algorithm in a training data set, so data that has already been seen by the algorithm, you can see that the confidence of the algorithms is high and that the prediction actually is correct. In this case, both algorithms said this is COVID-19. And then if you use unseen data, so that's data that's out of the area where you actually trained it on, then you can see that the confidence goes down and also the prediction is not always correct. And then an interesting thing, if you just show a picture that's completely unrelated, that doesn't even show a chest X-ray, then sometimes the confidence could still be very high, but the prediction is just completely off because it's not even a chest X-ray. So it's very important to have that heterogeneous data to make sure that the algorithms perform well. Besides having a small sample size, it is also very important for research purposes to anonymize or de-identify the data correctly. You will need that high quality, and with high quality, I mostly mean heterogeneous data to make sure to have that diversity in your data set. You will need structured data because if your data, the data that comes out of the PACS system, for example, is usually not very organized, and it's going to be very hard to use that raw data right away for your machine learning development. So you need to structure the data. And if you want to develop a supervised machine learning algorithm, you will need to label the data as well. And I will talk more about that during this presentation as well. So there are multiple steps that need to be taken to prepare data before it is ready for machine learning. And these 8 different steps is what I will walk you through during the rest of this presentation. So before you can get access to the unprocessed image data, you need to get ethical approval to be able to work with the data. So there are different approaches for getting ethical approval. You can, well, all of it always goes through the IRB. So usually this is a local institutional review board that evaluates your proposal. And you can say, okay, I will do a prospective study or I will do a retrospective study. So the prospective study is high quality. You can beforehand determine, I want to record these specific parameters, which is really great because you get exactly the kind of features, the kind of parameters that you are interested in. But the big disadvantage of prospective studies is it takes a long time before you actually have your data because you need to wait over time, especially if you want to have longitudinal data, like different changes over time of your imaging exam, for example. It is going to take a long time. It's going to be very expensive. So even though the quality of prospective studies is very good, it is very expensive, and therefore it is not used as much. We just learned in the last presentation that actually you see more and more trials or prospective studies coming up in the machine learning space, which is really great, good development. But most of the studies are still retrospective studies. So retrospective studies means you just look back, you grab the data that you can grab, which means that some parameters that you would like to have are not available or are only partially available. So that is a little bit of a problem there. The quality of retrospective studies is thus not as good, but it's much cheaper, and you have the data right away. Like, you don't have to wait for the data to be acquired over time. So that's an advantage over retrospective studies. Either way, if you want to do a prospective study or a retrospective study, you will need the IRB approval. Usually for a prospective study, you need informed consent from patients, and for retrospective study, this informed consent will be waived. So once you have your approval from your local institutional review board, you can start getting access to the data. So how do you get access to the unprocessed image data? Well, usually there are only a certain number of people that actually have access to the clinical data. So you need access to the PACS system, and usually it's the physicians, the technologists, sometimes it's the PACS managers and clinical scientists that also have access to the PACS systems. But very often it's not the actual AI developers that have access to PACS. So it's very important that there is a collaboration between the physicians and the AI developers, so that together they can work on developing the AI algorithm, as well as getting the right access to the exams that are needed for the AI development. So after getting access to the data, it's important to query the data, or to identify the right type of data that you will need for your specific exam. And this means that, for example, if you want to develop an algorithm to detect lung nodules on a chest CT scan, you will need to have a certain number of exams that are positive, that have lung nodules, and also some exams that are normal as control that don't have the lung nodules. So how do you identify that? Well, it's actually not that straightforward, because usually clinical data is stored for primary purposes. So it's very easy if I, as a radiologist, you just put in a medical record number or a date of birth and the name of the patient, and you'll identify that specific individual patient. But now we actually want to collect a cohort or a population of patients, and that makes it much harder. So there are specific PACS or risk search engines that allow for searching, for example, through radiology reports, using ICD-10 codes, or using CPT codes, for example. Not all PACS or risk systems have these kind of search engines, so it's not always available, and therefore there are other software packages available, including commercial as well as non-commercial packages. When I was still at Stanford, we were using STAR very often. So STAR is the Stanford Research Repository Tools. And there are 3 steps in the STAR method. First, there's cohort discovery. So you can put in your query, you can put in the specific search of the population that you're looking for. Let's say I'm looking for patients with lung cancer. I can identify them. Then I need to show the STAR system that I have an IRB approval. So you need to show the compliance. Once that's done, then you can actually get the chart review. So you can actually get information for the individual patients. The big disadvantage of this, it's not imaging based. So you're really looking for clinical just patients. But it could be that these patients maybe didn't even undergo a chest CT scan at Stanford, at my own institution. So then you cannot really use those patients. So it is a little bit complicated, because it's a clinical search method and not necessarily an imaging search method. So it might sometimes be better to use another system, a commercial system, or just to, it's going to be a little bit of extra work, because you have to check for all these patients what imaging data is available. So after you query the data, you need to make sure to de-identify the data properly. So according to HIPAA, which is what we're using in the United States, there are 18 PHI, or protected health information identifiers. And these include, for example, the name of the patient, the address of the patient, the date of birth of the patient, and those kind of things. So it's important to remove these 18 identifiers. And in medical imaging or radiology specific, people are using DICOM files. So DICOM files, they contain the pixel-based information, and then they also contain the headers, which is metadata. So the headers, for example, they contain information about the name of the patient, acquisition information like the slice thickness or the vendor of the machine that was used for acquisition of the images, and so on. So de-identifying the DICOM headers is relatively easy because usually they are relatively structured. You know in which tag is the name of the patient stored. So just remove all the tags from all the DICOM headers. The date of birth, for example, is usually a standard tag. So these things are relatively straightforward, although there are differences between different vendors and between different hospitals. It gets really complicated when there are identifiers embedded or burned into the images. So, for example, ultrasound exams very often have on the top the name of the patient, the medical record number, and these kind of things. So you need to make sure that this kind of information is removed from the image. And then you have to be careful with the images themselves. This is a 3D reconstruction of an RSNA Kaggle challenge data set that I just downloaded and made a 3D reconstruction. You can actually see some of the facial characteristics of this patient. So it is important to also look, especially if you're working with brain or head imaging, to make sure that images are not re-identifiable. So after the identification, it's time to transfer the data, and this can be done either to a local or to an external storage. It's not very easy because data is stored in silos. So it's hard to get it out. You actually do need to get it out before the AI developer can do something with it. So you can either store it locally or externally. Local storage is usually done for single center studies. If the AI developers are within that institution, then that's no problem. Then they can just work locally with it. And external storage is usually used for multi-center studies and for commercial AI development. So the pros of local storage are that the data is relatively safe. The data is easily available. It's all within the silo. And the pros for external storage are that it's relatively easy to share the data with other institutions, to back up the data. Usually this is done in the cloud, and the cloud will make an automated backup. So those are all pros. Cons for local storage are it is really hard to share the data outside your institution. So you have it within your local storage, but then how do you share it with other people? That is not super straightforward. And then for external storage, the costs are relatively high, and you will need a fast connection to actually work in the cloud, to actually work with all these data. So that's another disadvantage of external storage. So currently, what is usually done for AI development is centralized AI model development, and this is for multi-center studies. So let's say we're doing a study with 6 hospitals. What we're doing is we're de-identifying the data, we're curating the data within each hospital, and then we send it to a centralized data storage, and that is where we develop our machine learning algorithm. Another approach is federated learning, federated AI model development. So you still have your 6 hospitals, but instead of de-identifying the data and then sending it to a centralized data storage, we actually send the model to each different hospital and then train it on these smaller data sets and then send back the features, the parameters of the model. And that way you don't have to de-identify it. You don't have to send the data out of the silo. So those are big advantages. There are a lot of disadvantages, especially in medical imaging, because you have to make sure that, for example, the labeling is done similarly within each of these hospitals. It's hard if you don't actually see the images while you're developing your model, and there are many challenges with federated learning at the moment. So that's why the centralized AI model development is currently more common, but this is something that in the future could make a change. Okay, so once we've transferred the data, we can start with our quality control. So one thing is what we also experienced at SecMed, our startup, is medical data is very chaotic. So a lot of exams that are, for example, stored or characterized as chest x-rays might not be chest x-rays. So let's say I'm collecting a bunch of data and I want to develop a chest x-ray model, and this is what I'm finding. Then all of a sudden you see there are certain exams that are actually misclassified. So these are not chest x-rays. So it's important to really go through the different exams that you have to see, like, do I actually have the chest x-rays that I want? Or are there maybe some outliers, some misclassified exams in there as well? So that's something to really check before you actually, during your quality control assessment. Another thing is image quality. And this can go multiple ways. You can say, okay, I want to have only very good image quality, but then the problem is your algorithm will not work on lower image quality. So this is something that you need to assess yourself. Do I want this variability of image quality, or do I just want to have very good image quality for the images? So assess the images and see if it's representable of what you want to have. After quality control, we need to structure the data. I see I only have 3 more minutes, so I'll hurry up a little bit. So structure the data. For example, the DICOM headers can be very disorganized. Protocol names can range from CCT. If you, for example, want to do a study on cardiac CT, the protocol names, they can change from range from CCTA, coronary CTA, angiography. I mean, they all mean the same thing, but they're just different strings or different characters. So you have to make sure that this is all equalized so that you can really use this for your machine learning development. And for example, in terms of cardiac CT, you want to know whether there is ECG synchronization. So are we using prospective triggering or retrospective gating? Yes or no? And if so, what is the type of synchronization that we're using? So after structuring the data, we get to the last piece, and that's to label the data. So here, for example, you can see a chest CT scan that has a lung nodule. So there are different types of labels that we can use for this. For example, we can say a lung nodule is present or absent. So we just have a dichotomous label. Or we can say, okay, this lung nodule has a maximum diameter of 4 millimeters. So now we have a continuous scale label that gives us information about the size of the nodule. And then another thing, you can, for example, classify it as, oh, this is a benign nodule, or this is a non-small cell lung carcinoma, or something like that. So this could be different categories. And then you also have segmentation. So you can ask an expert to actually segment the lung nodule, which will give you coordinates, which gives you information about both the location as well as the size of the nodule, and may help with automated detection of lung nodules, for example. So there are different types of image labels that have different value. Retrospective annotation is most common and has actually the lowest value. So let's say I'm retrospectively gathering a bunch of chest X-rays, and I see, and I ask a radiologist to evaluate the chest X-rays, and then you get, some information. But it's not as good as when you do it, for example, in a prospective way, where the radiologist has information available from the electronic medical record, for example. So then you can actually specify, like, okay, I see something on the chest X-ray, and this is exactly what it is. So prospective annotation has higher value, but it's harder to get because you need to do it in a prospective way. The best quality image label that you can get is ground truth. So for example, in a lung nodule case, you want to have, if the biopsy was taken, you want to have the pathology report saying, like, this is a specific type of malignancy, for example, or you want to have lab values from blood lab tests. Or, for example, longitudinal information. If you know that the lung nodule decreased in size, then you know, okay, that was probably benign. Or if you have an outcome, like this patient died 3 years later of lung cancer, well, then you also have your answer. So ground truth is the highest quality, but also highest value, but also the most difficult to actually get. So how do you place your labels? Well, Daniel Rubin from Stanford, he actually developed EPAD, which is a platform where you can label images, but there are many other options available, 3D Slicer, Zyrex, ImageJ, that you can use to actually label or segment your images. You can do this either through crowdsourcing or through experts. Experts is most common. You ask 1 or 2 or 3 experts to label the images, but crowdsourcing is an interesting development as well. You just ask a bunch of non-expert people to evaluate images, and you would say, well, maybe that's not going to work very well. Actually, in certain cases, it can be helpful. For example, if you ask the crowd to segment abdominal organs, here you can see liver segmentations by non-experts, then you merge them, and then you do majority voting, making sure that everybody votes which segmentation do you think is right, and then the final segmentation is actually similar to an expert segmentation. So for a specific purposes like large abdominal organs segmentation, this works well. I can imagine that for specific lung tumors, it will be very hard to do these kind of crowd segmentations. Then you can also get labels out of your report. It would be great if you have structured reporting, because that makes it very easy to extract information from reports. Unfortunately, in reality, we usually don't have structured reporting. So a lot of people develop NLP algorithms to extract information out of reports, or just simply go through the reports and by hand pick out certain information, which is very often done in academic settings if you don't have a large data set. At Stanford, we faced some issues with segmentations. We developed a deep learning method to segment the true lumen, the false lumen, and false lumen thrombosis in patients with Stanford type B aortic dissections. We developed different methods, and what we found was, here you can see the original image. This is the ground truth, so segmentation done by a cardiovascular radiologist, and then we have two different models, and you can see that there are quite some discrepancies here, and the DICE scores were also not very good, especially for the false lumen thrombosis. And we found out that if we asked another expert to do these segmentations, we actually got quite different results as well. So you can imagine that if your ground truth is not correct, then your model is not going to perform very well either. So that was a big issue that we found out with this study. So if you look here, for example, in the testing set, the aortic segmentation was good. These are dissimilarity coefficients. The true lumen, the false lumen, and patent false lumen were okay, but then the false lumen thrombosis had a DICE coefficient of 0.5, so not very good. So that was an interesting result there. So at SegMed, as I mentioned before, we actually help with curating data. So if you are a researcher and you are interested in external validation, or just you need data, you can make an account on SegMed Insight. You can really build your own data set there of de-identified data. You can choose your modality, body area, where does the data have to come from, and search with ICD-10 codes, or search with specific disease names, for example. So that's if you want to do it the easier way. If you want to read more about data curation, you can read this paper that was published a few years ago between my colleagues at SegMed, Stanford, NIH, and UCL. So thank you for your attention, and I'm happy to take any questions.